Turn a glass slowly in your hand, and almost nothing seems to happen. The rim changes angle. A line of reflected light slides across the curved surface. The water inside tilts for a moment, then settles. The bubbles clinging to the inner wall rearrange themselves against the glass. Your fingers adjust their grip. Ordinary intuition says rotation is just a change in position. The object has been turned, nothing more. But physics finds something sharper inside that harmless gesture. The glass can rotate, the coordinate system can rotate, the experiment can be repeated facing north, south, east or west, and the deeper laws do not change. If they did, the consequences would not be subtle. A spinning planet could gain or lose rotational motion without cause. A figure skater pulling in her arms might not speed up in the same predictable way. A molecule rotating in space could obey one rule in one direction and another rule a few degrees later. The world would not merely look strange, its mechanical accounting would fail. Noether's theorem brings the sharper mechanism into view. It says that when a physical system has a continuous symmetry, there is a corresponding conservation law. If the laws do not change from one moment to the next, energy is conserved. If they do not change from one place to another, momentum is conserved. If they do not change when directions are rotated, angular momentum is conserved. What looks like a quiet indifference in nature becomes a measurable constraint. A change that does not change the law leaves behind something that cannot simply vanish. This is the first unsettling fact. Conservation is not just a rule attached to the universe from the outside, it is the shadow cast by symmetry. A glass on a table is not normally treated as an entrance into deep physics. It belongs to the small inventory of familiar things, transparent, cool, breakable, full or empty, near or far from the edge. Yet a simple rotation already separates appearance from law. The reflected line moves, but the water remains water. The mass does not change. The volume enclosed by the glass does not collapse. Gravity still points downward toward Earth. Molecules continue to collide, exchange energy, and press against the container. Something changes in description, but not in rule. Physics uses the word symmetry in a quieter way than ordinary speech. In daily life, symmetry usually means a visual balance, the two wings of a butterfly, a snowflake, a tiled floor, a pattern that can be folded, mirrored or rotated and still please the eye. Those symmetries are real, but they are only the surface of the idea. In physics, a symmetry is a transformation we can make without changing the underlying law. We can shift a system in space, we can rotate it. We can choose a different starting time. If the physical rule remains the same under that transformation, the theory has a symmetry. This kind of symmetry is not decoration. It is a statement about what nature refuses to care about. If an experiment is moved from one side of the room to the other, and the conditions are otherwise identical, we do not expect a new law of motion to appear. If the same pendulum is released today and tomorrow under the same conditions, we do not expect the date itself to change the equation. If we rotate our coordinate axes, the physical event does not become a different event. We have changed the description, not the world. This indifference is almost too familiar to notice. It sits underneath every repeated experiment. A chemist can compare results between laboratories because the rules are not tied to one sacred position in space. An engineer can build a machine from calculations because the laws do not change when the machine is turned around. A clock can be calibrated because time translation, at least for many local systems, does not rewrite the laws from one second to the next. Predictability begins with nature's refusal to assign different laws to arbitrary labels. But that refusal has a price, and the price is conservation. If the laws are the same under a continuous shift in time, energy cannot simply appear or disappear inside an isolated system. If the laws are the same under a continuous shift in space, momentum must be accounted for. If the laws are the same under continuous rotation, angular momentum is constrained. The invariance is not merely philosophical. It becomes a number that survives through change. A cup sliding across a counter slows down because friction transfers its organized motion into heat and microscopic vibration. To a person watching, the motion is gone. To physics, the energy has not been destroyed, it has been redistributed into the cup, the counter, the air, and faint sound. A rocket rises because exhaust is thrown downward at high speed, and the rocket gains momentum upward. It does not push against the emptiness of space. It balances a momentum account between itself and the material it expels. A spinning skater pulls her arms inward and rotates faster because the distribution of mass around the axis changes while angular momentum remains nearly fixed. These examples feel simple only because the accounting works so reliably. We grow up inside a world where conserved quantities behave like invisible rails. Motion can change, but not without exchange. Energy can become less useful, but not disappear from the total account. Rotation can speed up, but only through a change in how mass and motion are arranged. The laws are so stable that the mind treats them as background. Noether's theorem makes the background visible. It did not arise from a laboratory flash or a telescope image. It came from mathematics, from the attempt to understand what kind of structure a physical theory must have if its laws remain unchanged under certain transformations. At the centre of that understanding was Emmy Noether, one of the most important mathematicians of the 20th century. Her work did not add one more conservation law to an existing list. It explained why such laws appear at all. Noether entered physics from the side of structure. She was not trying to build a new instrument or measure a new particle. Her strength was seeing the hidden architecture beneath equations. At the time, physics was being reshaped by relativity. Space and time were no longer absolute containers. Gravity was no longer merely a force acting through a fixed stage. The language of physics had begun to change, and with that change came a question that could not be avoided. In the new theories, what exactly does conservation mean? This was not a minor bookkeeping problem. Energy, momentum, and angular momentum were already central to mechanics. They helped explain collisions, orbits, machines, heat, and waves. But Einstein's general relativity made space-time itself dynamic. If the background is no longer fixed, then older ways of talking about conserved quantities need to be examined carefully. Noether's theorem gave physics a deeper diagnostic tool. It showed that conservation laws are tied to symmetries of the action, the mathematical quantity whose variation yields the equations of motion. The word action can sound abstract, but its role can be heard without writing the equations. A physical theory often assigns a number to each possible history of a system. The actual motion is the one that makes that number stationary in a precise mathematical sense. This principle unifies many laws of motion. It is not that nature consciously chooses a path. Rather, the equations describing the path can be derived from this compact structure. When that structure has a continuous symmetry, Noether showed that a conserved quantity follows. This is the difference between noticing a pattern and proving a necessity. Before Noether, physicists knew many conservation laws. They used them with great success. After Noether, conservation was no longer a collection of separate facts. It became the mathematical consequence of invariance. The laws did not merely happen to conserve energy, momentum, or angular momentum. In theories with the right symmetries, they had to. Her life did not unfold in a world eager to honour that kind of contribution. Women in European academia face severe barriers to formal positions, lectureships, and recognition. Noether's ability was recognised by major mathematicians around her, but institutions often lagged behind the mathematics itself. She worked in conditions far less secure than her importance deserved. The story should not be made into a conspiracy or a myth of erasure. It is enough and more accurate to say that her name remained far less known outside specialist circles than the reach of her theorem would suggest. There is a strange quietness in that. Some scientists become public symbols because their discoveries attach easily to images. An apple, a telescope, a chalkboard equation, a dramatic experiment. Noether's discovery attaches to a relation. It does not sit in the hand. It is not visible through a lens. It lives inside the way modern theories hold together. It is used whenever physicists ask what a symmetry forces a system to conserve. A theorem can become so deeply embedded in science that it stops looking like a discovery and starts looking like part of the flaw. Return to the glass. If the glass is rotated a tiny amount, then another tiny amount, then another, the transformation is continuous. We are not jumping between two unrelated states, we are sliding smoothly through possibilities. This matters because Noether's theorem applies to continuous symmetries. A smooth change in time, position or orientation can leave the law unchanged. From that smooth invariance comes a conserved quantity. Time translation symmetry is the cleanest doorway into energy. If the laws governing a closed system are the same now as they are 1 moment later, the system has a form of time symmetry. The equations do not carry a special label saying that 1 second is physically privileged over the next. From that invariance comes conservation of energy. Energy is not conserved because it is a substance hidden inside objects. It is conserved because the mathematical structure of the theory does not change when the origin of time is shifted. That statement is easy to say and difficult to fully absorb. Energy is familiar because we pay for it, store it, burn it, measure it, waste it, and feel its absence in ordinary life. But everyday language often blurs useful energy with total energy. A battery runs down, a warm drink cools, a moving bicycle stops. In each case, usable energy has become dispersed. The ordered ability to do a particular kind of work has weakened, but in the broader physical account, energy has moved into heat. Sound, deformation, radiation, or microscopic motion. Conservation does not mean nothing changes. It means change must be paid for in another form. A falling book shows the accounting in miniature. Held above the floor, it has gravitational potential energy because of its position in Earth's gravitational field. As it falls, that energy becomes kinetic energy. When it strikes the floor and stops, the visible motion disappears. But the energy has not vanished into a gap in reality. It has entered the floor and the book as tiny vibrations, heat, sound waves, and deformation. If the accounting seems to fail, the usual reason is that the system has been drawn too narrowly. This habit of widening the system is one of the quiet disciplines of physics. If energy appears to disappear, look for where it went. If momentum seems to fail, ask what received the impulse. If angular momentum seems to change, search for an external torque or an overlooked part of the system. Conservation laws make physicists suspicious of incomplete descriptions. They do not prevent complexity, they make complexity traceable. Spatial translation symmetry gives momentum. If the laws are the same here as they are there, provided the physical conditions are carried along, then the theory does not privilege one location over another. Momentum conservation follows. When two bodies collide, their individual motions may change dramatically, but the total momentum of the closed system remains fixed. A billiard ball transfers motion to another. A gun recoils when a bullet moves forward. A person walking pushes the ground backward, and the ground pushes the person forward through friction. In every case, motion is not created in isolation. It is exchanged. The recoil of a firearm is a blunt example, but it reveals the account clearly. The bullet leaves with momentum in one direction. The gun and shooter receive momentum in the other direction. The masses and velocities differ, so the motions look unequal, but the total balance is constrained. A rocket is the same principle freed from the need for ground or air. It throws mass backward and moves forward. Empty space gives it nothing to push against, and it does not need anything. Momentum conservation is enough. Walking is softer, almost too ordinary to notice. The foot presses backward against the ground. Static friction allows the ground to exert a forward force on the body. On ice, where friction is reduced, the same muscular effort produces less controlled motion. The body has not forgotten how to walk. The momentum exchange with the surface has become unreliable. A familiar action turns into a lesson in symmetry. The laws do not depend on where the step is taken, but the conditions decide how momentum is transferred. Rotational symmetry gives angular momentum. If the laws do not change when the whole coordinate system is rotated, no direction in empty space is given a special mechanical privilege. From that invariance comes the conservation of angular momentum. This quantity measures rotational motion, but not simply spin speed. It depends on how mass is distributed relative to an axis and how fast it moves around that axis. A skater tightening a spin makes the principle visible. With arms extended, mass is spread farther from the axis. When the arms are pulled inward, the same angular momentum is carried by a smaller rotational distribution, and the angular speed increases. No hidden engine has appeared. Muscles do work and friction acts, so real systems are never perfectly ideal, but the central relation is visible with the naked eye. Change the distribution, and the rotation responds because the angular momentum account must be preserved. Orbits reveal the same logic on a larger scale. A comet moving around the Sun travels faster when it's closer and slower when it's farther away. Part of this behaviour can be described through conservation of angular momentum. As the distance to the Sun changes, the tangential speed adjusts so the rotational account remains consistent, assuming no major external torque. The orbit is not a random curve. It is a path constrained by gravity, energy, and angular momentum together. At the scale of galaxies, the story becomes more complex. Stars, gas, dust, dark matter, gravitational interactions, and long histories of merging all contribute. Yet angular momentum remains one of the organising quantities in understanding why rotating disks form and why collapsing matter does not simply fall straight inward. A small initial rotation can become a vast structure because collapse changes distances while conservation constrains motion. A galaxy is not a skater, but the same kind of accounting survives in a much richer system. Even the microscopic world carries rotational accounting, though it must be treated carefully. Electron spin is not a tiny ball spinning around an axis. That image breaks down quickly. Spin is a quantum property with angular momentum-like behaviour and immeasurable magnetic consequences. It shapes atomic structure, chemical behaviour, and magnetic materials. The old picture of rotation cannot simply be carried into quantum mechanics, but the symmetry behind angular momentum still reaches there. The law has changed language, not vanished. This is one reason Noether's theorem feels so deep. It crosses scales without becoming vague. It touches a hand turning a glass, a rocket in vacuum, a planet in orbit, and quantum particles in magnetic fields. The physical forms differ, the mathematics becomes more demanding. But the same relationship keeps appearing. Invariance produces conservation. The ordinary world would be nearly unknowable without this relationship. If energy were not conserved in isolated systems, stars might brighten or fade without an account of their fuel, engines could gain output without input, and chemical reactions could lose track of their thermal and binding energy. If momentum were not conserved, collisions could produce motion from nowhere. If angular momentum were not conserved, rotating systems could speed up or slow down without torque. The problem would not be that physics became surprising. The problem would be that physical prediction would lose its spine. Instead, nature permits transformation without permitting arbitrariness. Heat spreads, light scatters, sound fades, structures break, fuel burns, bodies collide. But through these changes, certain quantities remain tied to the symmetries of the laws. This is the calm intensity of conservation. It is not loud. It is not decorative. It is what prevents change from becoming lawless. The theorem also changes how we think about a law of nature. A law is not merely a sentence saying what objects do. It is a structure that remains consistent under transformations. If a theory changes its predictions when we merely rename coordinates, shift the origin of time, or rotate an axis in an otherwise identical situation, the theory is not describing only the world, it is smuggling in something arbitrary from our description. Symmetry strips away those arbitrary labels and asks what remains physically meaningful. This is why the concept became so central to modern physics. Theories are judged not only by the quantities they predict, but by the transformations they respect. A symmetry can forbid certain processes, require certain conservation laws, and guide the form of possible interactions. In that sense, symmetry is not a painted pattern on top of the theory. It is more like a load-bearing wall inside it. The strange part is that the load-bearing wall is often invisible. A person sees a glass rotate, not rotational invariance. They see a skater spin faster, not the symmetry of space. They see a rocket rise, not spatial translation symmetry. They see a warm object cool, not the time independence of the laws that supports energy conservation. Physics takes these familiar events and shows that their reliability comes from something less visible than the events themselves. That movement from the visible to the structural reveals the deeper puzzle. We live in a world filled with changes, yet some accounts refuse to close incorrectly. The form of motion alters, but total momentum is constrained. Energy becomes less useful, but it does not fall out of the universe. Rotation responds to changing shape, but angular momentum keeps its balance. Beneath the motion is a refusal. Certain transformations do not change the law, and because they do not, certain quantities cannot simply disappear. For a long time, this might seem like a completed picture. Symmetry gives conservation. Conservation gives stability. Stability gives predictability. The world becomes intelligible because its laws do not care about arbitrary shifts in time, space, and orientation. But modern physics did not let the picture remain that simple. The stage on which these symmetries operate stops behaving like a fixed stage. In classical mechanics, it is natural to imagine space and time as the background against which everything else happens. Objects move through space. Clocks measure time. Forces alter motion. Under those assumptions, time translation, space translation, and rotation have a clean intuitive meaning. Shift the experiment, turn the apparatus, start the clock later. The background remains there, stable and waiting. General relativity altered that background. Einstein's theory did not describe gravity as an ordinary force acting inside a rigid arena. It described gravity as the curvature of space-time itself. Matter and energy shape space-time, and space-time guides matter and light. A planet follows a natural path through curved geometry. A clock runs differently in a stronger gravitational field. Light bends near massive bodies because the straightest available path is not the one Euclidean intuition expects. This shift changes the question of conservation. If space-time were a fixed stage, we could ask how much energy the actors carry on it. But if the stage itself is dynamic, if its geometry changes in response to the actors, and then changes their motion in return, the accounting becomes more delicate. Energy still matters. Momentum still matters. But the simple global bookkeeping familiar from many classical systems no longer transfers automatically to every possible space-time. The issue becomes sharp in cosmology. Light travelling through an expanding universe is stretched. Its wavelength grows. A longer wavelength means lower photon energy. In ordinary local physics, if a photon loses energy, one asks where the energy went. Was it absorbed by matter? Did it heat something? Did it transfer motion? In an expanding universe, that question becomes more subtle because the space-time as a whole may not have the time translation symmetry needed for a simple, global conservation law of energy in the familiar sense. This is not a failure of physics. It is Noether's theorem doing its job. If energy conservation in the usual form is tied to time translation symmetry, then a space-time that changes with cosmic time does not automatically provide the same symmetry. The local equations still maintain a precise form of conservation for energy and momentum flowing through space-time. Objects do not gain or lose energy arbitrarily in small regions. But the total energy of the entire expanding universe is not always a well-defined quantity in the simple way a beginner's mechanics problem might suggest. This is a serious refinement, not a loophole. It tells us that conservation laws are not magic phrases. They have conditions. They depend on the symmetries of the system being described. When those symmetries are present, the conservation law has a precise form. When those symmetries are absent or altered, the law must be stated more carefully. The theorem that once made conservation feel more secure now also tells us where naive conservation language becomes unsafe. A photon redshifting across cosmic expansion is not a violation of energy conservation in the ordinary sense, because the ordinary global energy account may not exist for that whole space-time. The photon's energy is measured relative to observers, and those observers live inside an evolving geometry. The expansion is not a substance stealing energy. It is a change in the space-time background that changes what the energy of the travelling light means relative to cosmic observers. This is the kind of subtlety that makes the subject feel almost unstable. The familiar conservation law remains powerful in a laboratory, an engine, a collision, or a local gravitational system. Yet when the scale expands to the entire universe, the same words must be sharpened. Energy is not a simple cosmic coin stored in one universal vault. Its conservation depends on the structure of time in the theory, and time itself is part of space-time geometry. Noether's theorem therefore does two opposite things at once. It explains why conservation laws are so strong, and it prevents us from using them carelessly. It gives energy a deeper origin, but also warns that energy conservation in its familiar form requires the right symmetry. It unifies mechanics, but also reveals why general relativity demands a more careful language. The theorem is not only a key that opens a door, it is also the measuring tool that tells us when we have walked into a different room. The kitchen glass remains calm because it sits in a local region where the relevant symmetries work well enough for ordinary physics. The table is not expanding away from your hand with the universe. The glass is not sitting near a horizon or inside a violent gravitational field. Its rotations and translations are described with familiar tools. Energy, momentum, and angular momentum remain excellent accounts for practical purposes. The deeper complication does not erase the ordinary world. It explains why the ordinary world is a special, stable case. This distinction is important. Modern physics does not destroy common sense by declaring it false everywhere. It shows where common sense earned its reliability and where it must stop pretending to be universal. In a small laboratory over a short time, the laws look time-independent, space looks uniform, rotations behave normally. Noether's theorem gives the conservation laws we expect. Across a dynamic space-time, the geometry itself becomes active, and the symmetry conditions must be checked rather than assumed. There is a quiet physical consequence here. The universe is not merely a collection of objects using conservation laws. It is a system whose very space-time structure determines which conservation statements can be made globally. The rule is not written above space-time. It is tied to space-time's symmetries. If the geometry changes, the account changes with it. Here the picture changes. Symmetry began as a kind of invariance hidden in ordinary gestures. It became the source of conservation laws. Then gravity revealed that the background on which we define those symmetries is not always fixed. The same theorem that makes energy conservation feel inevitable in one setting tells us why the meaning of energy becomes subtler in another. The universe is accountable, but the form of the account depends on the structure of the ledger. From here, symmetry no longer looks like a simple visual idea or even just a path to familiar conservation laws. It begins to look like a deeper grammar for physical theory. It tells us which changes are merely changes of description, which changes have physical consequences, and which quantities must be protected when the laws remain indifferent to a transformation. Yet as soon as space-time itself becomes dynamic, the grammar must become more precise. What does it mean for nature to keep an account, when the page on which the account is written can also bend? The bent page changes the meaning of the account. In ordinary mechanics, we can imagine a fixed background, a silent grid on which bodies move and forces act. The ledger is laid flat. Positions can be marked, velocities can be calculated, energy can be assigned to moving bodies, raised bodies, heated bodies, compressed springs, chemical bonds and fields. If something seems missing, we search the surroundings. The method is powerful because the stage itself does not enter as one of the moving entries. But general relativity made the stage active. The geometry of space-time is no longer just the place where energy is counted, it is part of the count. Matter and radiation influence curvature. Curvature changes the motion of matter and radiation. A clock far from Earth and a clock near Earth do not measure time in exactly the same way. A beam of light crossing a gravitational field does not keep the same relationship to time and energy for every observer. The ledger is not false, but it is written on something that can curve, stretch, and evolve. This does not destroy conservation. It makes conservation more exacting. In a small enough region of space-time, physics still demands a local balance. Energy and momentum do not simply appear from nowhere in a laboratory, because the universe is expanding far away. A collision inside a detector still has to account for what entered and what left. A particle decay still obeys conservation laws. A star still shines because nuclear processes convert mass energy in ways that can be calculated. Local physics remains disciplined. The subtlety appears when we ask for one total account of an entire dynamic spacetime. The question sounds simple, only because everyday experience trains us on systems that are small, isolated and set inside a nearly fixed background. Once the background itself evolves, the symmetry supporting the familiar account may not exist globally. If there is no single time translation symmetry for the universe as a whole, then the usual global energy conservation law cannot be carried over unchanged. Noether's theorem has not failed. It is telling us that the conditions for the familiar statement have changed. From this comes a stricter lesson. Conservation is not a slogan, it is a relation between structure and symmetry. To know what is conserved, one must know which transformations leave the theory unchanged. The deeper the theory becomes, the less safe it is to assume that a familiar word keeps the same meaning everywhere. Energy in a falling book, energy in a gravitational wave, energy in an expanding universe, and energy in a quantum field are connected ideas, but not identical pieces of a simple cosmic currency. The same precision that complicates energy in curved space-time opened another path. If symmetries can generate the conservation laws of motion, perhaps they can do more. Perhaps they can determine not only how bodies move, but what kinds of interactions are possible. Perhaps the forces themselves are not merely added to matter, but arise because the description of matter has hidden freedoms that must be respected. To enter that layer, the old image of tiny objects moving through empty space has to soften. In modern physics, the basic language is not only particles but fields. A field is a physical quantity spread across space and time, capable of storing energy, carrying disturbances, and interacting with other fields. The electromagnetic field is the easiest to feel indirectly. A changing electromagnetic field can travel as light. A magnetic field can turn a compass needle. An electric field can accelerate a charged particle. Radio waves, lasers, microwaves, visible light, and X-rays are all expressions of one electromagnetic structure at different frequencies. Quantum field theory changes the picture again. In this language, what we call particles are quantized excitations of fields. An electron is not best imagined as a tiny solid bead inserted into space. It is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks, neutrinos, and other particles belong to their own fields. A detector click is a localized event, but the theory underneath is not a collection of miniature pebbles. It is a set of fields whose excitations behave particle-like when they are created, destroyed, scattered, or measured. This is not a poetic shift. It is the language that allows modern physics to compute particle collisions, atomic energy levels, magnetic behavior, radiation, and the forces acting at subatomic scales. The world of tables and water and hands does not disappear. It becomes the large-scale pattern produced by fields and their rules. Matter feels solid because electromagnetic interactions and quantum principles prevent atoms from collapsing into one another in the way a naive mechanical picture might expect. Chemical bonds form because electron states and electromagnetic forces allow stable arrangements. Light is emitted because fields exchange energy in quantum units. Once fields become central, symmetry becomes more than a statement about turning objects or shifting experiments. It becomes a statement about the allowed descriptions of the fields themselves. A field can have mathematical components that are not directly visible as separate physical facts. We may change certain parts of the description without changing anything measurable. Such freedom sounds like a redundancy, and in one sense it is. But in physics, a redundancy can become powerful if it is imposed consistently. This is the doorway to gauge symmetry. The word gauge has an ordinary origin, a choice of scale, a way of measuring or calibrating. In physics, a gauge symmetry means that different mathematical descriptions can represent the same physical situation. If two descriptions differ only by a gauge transformation, they are not two different worlds. They are two ways of writing the same world. The measurable quantities must not depend on that arbitrary choice. At first this sounds like bookkeeping, but the requirement becomes physically demanding when the freedom is local. A global change applies everywhere in the same way. A local change can vary from point to point in space and time. If a theory is required to remain unchanged under such local transformations, it often must include a field that compensates for the changing description. What looks like a mathematical freedom becomes the reason an interaction field must exist. Electromagnetism gives the cleanest example. The quantum state of an electron has a phase, a kind of internal angle in the complex mathematical description. If we change that phase by the same amount everywhere, measurable probabilities do not change. But if we allow the phase change to vary from place to place and time to time, the theory needs a way to compare phases across spacetime consistently. The electromagnetic field enters as the compensating structure. It allows the local freedom to exist without changing the physical predictions. This is a difficult idea because it reverses the order of common intuition. We tend to imagine that particles exist first, then forces are added between them. But gauge theory suggests a deeper relation. If the matter field has a certain local symmetry, then an interaction field is required to preserve that symmetry. The electromagnetic force is not simply a mysterious influence pasted onto charged particles. It is tied to the demand that the description of charge fields may be changed locally without changing the measurable physics. From this gauge, symmetry comes a conservation law, conservation of electric charge. Charge is not just a small label attached to an electron like a tag on luggage. It is connected to the symmetry structure of the field. Electrons, positrons, photons, atoms, currents, and radiation all obey rules shaped by this structure. A process may transform particles, but it cannot violate the total electric charge. An electron and a positron can annihilate into photons because their charges cancel. A photon can help produce a particle-antiparticle pair under the right conditions, but the pair must carry charges that sum to the original total. The account is protected. Charge conservation is so reliable that its depth can be easy to miss. We're used to the idea that an object can become electrically charged by gaining or losing electrons. We see sparks, batteries, lightning, currents in wires. But underneath those visible effects is a strict rule. The total electric charge in an isolated system remains constant. Noether's theorem connects that rule to symmetry. In the quantum field description, the conservation of charge reflects an invariance of the underlying action under a continuous transformation of the field. Again, what changes without changing the law leaves something behind that cannot vanish. Electromagnetism is only the first case. The modern standard model of particle physics is built from gauge symmetries. Its structure includes symmetries associated with the electromagnetic, weak, and strong interactions. The strong interaction binds quarks into protons and neutrons and holds atomic nuclei together through residual effects. The weak interaction governs processes such as beta decay, in which one type of particle can transform into another. These forces are not arbitrary additions. They arise in theories organized by gauge principles where fields and interactions are constrained by symmetry. The strong force is described by a gauge theory called quantum chromodynamics. Its charges are not electric charges but color charges. The word color here is not visual color. Quarks do not carry red, green or blue in the sense of light reaching the eye. These labels name three types of strong charge. Gluons, the force carriers of the strong interaction, also carry color charge, which makes the theory highly self-interacting. Unlike photons, which do not carry electric charge, gluons interact with one another because they participate in the charge structure they mediate. This has a dramatic physical consequence. Quarks are not found freely isolated under ordinary conditions. The strong force behaves in a way that confines them inside composite particles, such as protons and neutrons. Pulling quarks apart does not simply weaken the force into nothing, as one might expect from familiar long-range forces. The energy stored in the strong field can grow until new particles form. The attempt to isolate a quark produces more hadrons instead of a lonely quark emerging cleanly. Here, symmetry does not create a gentle, visible balance. It creates a world where the particles making up ordinary nuclei are permanently hidden inside bound states. Every atom in your body depends on this. The protons and neutrons in atomic nuclei exist because quarks are held together by a gauge field, whose structure is dictated by a non-abelian symmetry. The word non-abelian means, in part, that the order of certain transformations matters. The mathematics is abstract. But the physical result is concrete. The strong force has a self-interacting character unlike electromagnetism, and that character helps make stable nuclear matter possible. The weak interaction reveals another side of symmetry. It can change one type of particle into another. In beta decay, for example, a neutron can transform into a proton while emitting an electron and an antineutrino. Inside that process, a down quark changes into an up quark through the weak force. The weak interaction is essential in nuclear reactions, radioactive decay, and the processes that allow stars to shine in particular ways. Without it, the particle world would have a different set of possible transformations, and the chemistry of the universe would not lead to the same cosmic history. Yet the weak force looks very different from electromagnetism. It is short-range because its force-carrying particles, the W and Z bosons, are massive. The photon is massless, so electromagnetic effects can extend across large distances. The weak bosons are heavy, so weak interactions are confined to extremely small scales. But in the deeper electroweak theory, electromagnetism and the weak interaction are connected. They emerge from a unified gauge structure whose symmetry is hidden, or broken by the Higgs field. Spontaneous symmetry breaking is one of the most subtle mechanisms in physics, because the laws can have a symmetry that the state of the system does not display. A simple analogy is a pencil balanced perfectly on its tip. The situation is rotationally symmetric before the pencil falls. No horizontal direction is privileged, but when it falls, it chooses one direction. The underlying setup may be symmetric, while the realized state is not. The analogy is imperfect, but it captures the distinction between the symmetry of the law and the symmetry of the outcome. The Higgs field fills space with a non-zero value. Particles interacting with this field can acquire mass. In the electroweak theory, the symmetry structure is not simply absent. It is hidden by the state of the Higgs field. The W and Z bosons become massive, while the photon remains massless. The result is the world we observe: short-range weak interactions and long-range electromagnetism. What looks like a sharp difference between two forces at ordinary energies is tied to a deeper symmetry and the way that symmetry is expressed. Here, symmetry changes its role again. Symmetry is not always visible as sameness. Sometimes it is present in the equations but hidden in the state. Sometimes the world looks asymmetric precisely because a symmetric law has settled into a particular configuration. The broken symmetry is not a failure. It is a mechanism. It determines masses, ranges of forces, and the structure of particle interactions. The universe can hide a symmetry by choosing a state. This is not only a particle physics lesson, it occurs in many physical systems. A magnet above its Curie temperature has atomic magnetic moments, oriented randomly, producing no preferred direction overall. Below that temperature, the system can settle into a state where many magnetic moments align. The laws do not pick one universal direction for the magnetization, but the material does. A symmetry present in the high-temperature state becomes broken in the ordered phase. The material acquires a direction because the state has chosen one among many equivalent possibilities. Water freezing into ice is another kind of ordering. Liquid water has molecules moving and rearranging freely. Ice forms a more rigid crystalline structure, reducing the continuous freedom of the liquid into a patterned arrangement. The laws of molecular interaction have not changed, but the state of the matter has. Phase transitions show that symmetry can be lost or gained as conditions shift. The same microscopic rules can produce different macroscopic forms. In the early universe, such transitions may have been more than laboratory curiosities. As the universe expanded and cooled, fields and forces may have passed through changes in symmetry. What appears at low energy as separate interactions may have been more unified at high energy. Some symmetries may have been restored in the hotter early state and broken as the cosmos cooled. This idea is not a license to invent details without evidence, but it is a central organizing principle in high-energy physics and cosmology. Temperature, field values, and symmetry are linked. The deeper we go, the less symmetry looks like visual order. It becomes a generator of law, a protector of conservation, a source of forces, and a mechanism for hidden unity. The world's visible complexity may come from laws with symmetries that are exact, approximate, broken, local, global, space-time based, or internal. A glass rotation is only the beginning. The same logic extends to the transformations of quantum fields that no eye can see. Internal symmetries are especially strange because they do not correspond directly to moving an object in ordinary space. They act on the mathematical identity of fields. A rotation in physical space turns a glass. An internal transformation may rotate components of a field into one another in an abstract space of possible states. Yet the consequences are measurable. Particle charges, allowed interactions, conservation laws, and force carriers all depend on such structures. It is tempting to say that symmetry is the hidden code of the universe. The phrase has force, but it needs discipline. Physics has not shown that the universe is literally written like human software, nor that there is a programmer-like layer behind the equations. What symmetry provides is not code in the everyday technological sense. It is a constraint structure. It tells physical descriptions which changes are redundant, which quantities are conserved, and which interactions are allowed. It is not a metaphorical secret message, it is a mathematical condition with experimental consequences. The reason the code metaphor appears at all is that symmetry behaves like a rule deeper than the visible object. A charged particle may come and go in a detector, a field may fluctuate, a force may act through a particle exchange, but the allowed transformations remain in the theory. They restrict what can happen even before a specific event occurs. In that limited sense, symmetry resembles grammar more than machinery. It does not write a sentence by itself, but it determines which sentences are possible. Grammar is a safer image than code because it does not imply a machine running behind the stars. A language can produce many sentences, but not every sequence of words is allowed. A physical theory can produce many processes, but not every imaginable process has non-zero probability. A decay may be forbidden because it would violate charge conservation. A scattering event may be allowed only if energy and momentum can be balanced. A force may exist only because a gauge symmetry requires a field to preserve local consistency. The world is not free to happen in every way. This gives physical law a strange austerity. Nature is not simply full of things, it is full of prohibitions. A proton does not decay in the simplest ways if doing so would violate observed conservation rules and symmetries. An isolated electric charge cannot vanish into neutral photons. A particle interaction must respect energy, momentum, angular momentum, charge, and other quantum numbers depending on the theory. Much of reality's stability comes not from what pushes, but from what is forbidden. That stability can be dramatic. Atoms persist because electrons occupy quantum states according to strict rules, including the Pauli exclusion principle. Nuclei persist because strong interactions bind protons and neutrons, while other processes are constrained. Chemical identity persists because electric charge, quantum states, and electromagnetic interactions do not behave arbitrarily. The large-scale reliability of matter depends on a web of microscopic restrictions. A stone does not hold its shape because it is a simple lump of substance. It holds because fields and symmetries leave only certain stable arrangements available. At the same time, symmetries are not always exact in the same way. Some are fundamental in current theories, some are approximate, emerging in certain limits. Some are broken by interactions that are weak but real. A conservation law that seems perfect in one domain may be violated in another if the associated symmetry is only approximate. Particle physics is full of such distinctions. The art is not merely finding a symmetry, but knowing whether it is exact, approximate, global, local, broken, accidental or emergent. This careful classification matters because false symmetry can mislead. A pattern may look conserved only because the processes that violate it are rare or inaccessible at ordinary energies. Conversely, a symmetry may be hidden so deeply that only high-energy experiments reveal its structure. Physics moves between these possibilities by measurement. It asks not only what the theory permits, but what nature actually does. There is another twist. Some symmetries are not merely helpful. They can be required for consistency. Gauge symmetries remove unphysical degrees of freedom from the description. Without them, the theory might count mathematical artifacts as real particles or produce predictions that fail basic requirements. In this sense, gauge symmetry is not just a decorative invariance that happens to generate a force. It is part of what makes the theory physically coherent. A photon, for example, has polarization states. The electromagnetic field can be described by potentials, but not every component of those potentials corresponds directly to a physical degree of freedom. Gauge freedom ensures that different potential descriptions leading to the same electric and magnetic fields are treated as the same physical situation. The redundancy prevents us from mistaking description for reality. It tells us which parts of the mathematical apparatus are labels and which parts can be measured. This is one of the deepest lessons of modern theory. Reality may be less than the raw description. A mathematical representation can contain extra structure that helps calculation but does not correspond to independent physical facts. Gauge symmetry identifies that extra structure. It says that two configurations that look different in the equations may be physically identical if they are related by a gauge transformation. The true physical content is what remains invariant. The search for invariance is older than quantum field theory, but gauge theory makes it sharper. Electric and magnetic fields, phases around loops, scattering amplitudes, conserved charges. These are quantities that can survive changes of description. In a world where coordinates can be chosen freely, phases can be redefined, and fields can be represented in multiple ways, physics must cling to what does not depend on arbitrary choices. Symmetry tells it where to hold. This is why the subject can feel both abstract and concrete at the same time. The abstract part involves transformations, groups, fields, and actions. The concrete part is a detector registering a particle, a current flowing in a wire, a nucleus decaying, a laser emitting photons, a magnet aligning, a star producing neutrinos. The events are measurable because the underlying rules are constrained. The abstraction is not floating above reality. It is the scaffolding that allows reality to be predicted. From here, the idea of conservation expands into something broader: protection. A conserved quantity is protected against change by a symmetry. A massless photon is protected by gauge structure. Certain quantum states can be protected by topological features or symmetry constraints. In condensed matter physics, phases of matter may be distinguished not only by visible order, but by patterns of entanglement, topology, and symmetry. The word protection becomes more than a metaphor. It describes why some features survive perturbations that might otherwise destroy them. A topological feature is one that cannot be removed by small, smooth deformations. A knot cannot be untied without passing a strand through another or cutting it. A hole in a surface cannot vanish if the surface is only stretched and bent. In physics, topology can protect certain states or modes, because local disturbances cannot easily erase a global property. This is another form of stability through structure. The system is not protected because each microscopic piece is untouchable. It is protected because the relevant information is stored in a way that local damage cannot simply delete. Now the language begins to approach information. Information in physics does not mean human meaning, belief, or consciousness. It means the distinguishability of physical states, the correlations between systems, and the constraints on what can be inferred or transformed. A hot gas contains microscopic information about the positions and velocities of its molecules, even if no human can practically recover it. A quantum state contains information about possible measurement outcomes. A field configuration contains information about charges, excitations, and correlations. Information is physical because it is carried by physical states. The connection to symmetry is not accidental. Symmetry tells us when two descriptions should count as the same. Information tells us what distinctions remain physically meaningful. If a transformation changes only a gauge choice, it has not changed the physical information. If a transformation changes an invariant quantity, it has. The line between redundancy and reality is drawn by symmetry. This is a quiet but important shift. Earlier, conservation seemed like the main prize. Now the deeper issue is what physical distinctions can exist at all. A gauge transformation may alter the written form of a field without altering the world. A true interaction changes physical information. A conserved charge labels a distinction that cannot be erased by allowed processes. A broken symmetry allows the state of a system to carry an order that the laws did not select in advance. Symmetry is not only about what remains constant, it is about what counts as a real difference. In ordinary life, differences are obvious. A glass is here, not there. The water is warm, not cold. The light is on, not off. But at the level of fields and symmetries, some differences in description are not physical, while some invisible differences are extremely physical. Changing a gauge may look like a change in equations and yet do nothing measurable. Changing a charge changes what interactions are possible. Changing a phase locally without the proper gauge field breaks consistency. The apparent and the real separate. This separation becomes crucial in quantum theory. A quantum state can contain phase relationships that do not show up as ordinary visible features but control interference. Two paths may lead to the same detector, and the amplitudes associated with them may add or cancel depending on their phase. The measurable pattern depends on relationships that are not directly seen in a single classical trajectory. Physics becomes a study of hidden relationships made visible through outcomes. The Aharonov-Bohm effect captures this with unusual clarity. In that effect, charged particles can be influenced by electromagnetic potentials in a region where the magnetic field is zero along their path, because the particles encircle a region containing magnetic flux. The measurable interference pattern depends on a gauge invariant quantity associated with the loop. The local force picture is not enough. The physical content lies in a relation around a path, not just a push at a point. This kind of phenomenon forces a more careful imagination. The electromagnetic potential is not simply a disposable mathematical convenience, yet its individual values are gauge-dependent and not directly physical in isolation. What matters are the gauge-invariant relationships. A loop can carry physical information even when no classical force acts along the path. Symmetry again tells us which quantities are real. At this stage, the earlier glass has become almost unrecognizable. The rotation that began as a visible transformation has led to an invisible hierarchy. Space-time symmetries, conservation laws, dynamic geometry, quantum fields, gauge freedom, internal transformations, charges, forces, and the difference between physical information and descriptive redundancy. The path is long, but each step is compelled by the same question. What can change without changing the law? And what must remain when that kind of change is allowed? The answer is no longer only energy, momentum, and angular momentum. It includes electric charge, color charge, weak quantum numbers, gauge invariant phases, protected states, and the allowed structure of interactions. Symmetry has moved from the furniture of the world into the grammar of the microscopic. It no longer merely explains why a rotating object behaves predictably. It helps explain why matter has the kinds of interactions from which objects can exist. A more delicate difficulty begins here. If symmetry can protect conserved quantities, if gauge structure can protect physical consistency, and if topology can protect certain global features from local disturbance, then stability in physics may often depend on information being stored non-locally or redundantly. Not in the human sense of a message hidden in a box, but in the physical sense that a system's important distinctions are not always confined to one small part. A crystal's identity is not stored in one atom. It appears in the pattern across many atoms. A magnet's direction is not the property of one isolated spin, but of collective alignment. A quantum phase may be defined by entanglement or topology, spread through a system. A conserved charge belongs to a whole closed system, even if it is carried by many particles. the physical account can be distributed. This brings us toward the mathematics of error correction, but the approach has to be slow. Error correction is not evidence that the universe is a computer. It is a general strategy for preserving information against disturbance. A simple classical code might store a bit redundantly so that one error can be detected and corrected. A quantum error-correcting code does something more subtle, because an unknown quantum state cannot be copied directly. Instead, the logical information is encoded into correlations among several physical systems so that certain local errors can be diagnosed and reversed without measuring and destroying the encoded state. The remarkable thing is not that engineers use such codes. The remarkable thing is that similar structures appear in theoretical physics when stability, symmetry, and locality are pushed to their limits. A quantum system can protect information by spreading it into correlations. A local disturbance may damage a piece without erasing the encoded whole. The information is not sitting in one place in the ordinary sense. It is held by a pattern. Once this idea is heard, it begins to resonate with earlier themes. A conserved quantity is not always located in one object. It belongs to a closed system. A gauge-invariant fact is not always visible in one component of a field. It belongs to a relationship. A topological feature is not erased by small local damage because it is a property of the whole configuration. The stable thing is often not the local mark, but the global structure. This is the point where physics begins to sound strangely close to information theory, and where the danger of exaggeration rises. The careful claim is narrow but powerful. The mathematics of preserving information against local disturbance has become important in understanding certain quantum systems, and in some theoretical contexts it appears connected to the structure of space-time and gravity. The careless claim would be that reality is proven to be a computer. That has not been shown. The deeper and cleaner statement is that nature, like any system with stable physical distinctions, must have ways for structure to survive change. The world is noisy. Molecules collide, fields fluctuate. Quantum systems interact with environments. Radiation spreads. Heat degrades organized motion. If anything stable exists, an atom, a charge, a phase of matter, a law-like pattern, then some structure must protect it against the constant pressure of disturbance. Symmetry is one form of protection. Topology is another. Redundant quantum encoding is another. Each reveals a different way in which what matters physically may be less fragile than its individual pieces. This is not only an abstract concern. The entire visible world depends on protected structure. Electric charge conservation keeps charged processes accountable. Gauge symmetry shapes force laws. The Pauli exclusion principle helps give matter its stability. Energy conservation organizes transformations. Angular momentum conservation shapes rotation from atoms to galaxies. Without these protections, matter would not simply behave differently. It might fail to form stable, knowable structures at all. The reversal is quiet rather than dramatic. At first, conservation laws looked like rigid bookkeeping. Then symmetries showed why the bookkeeping exists. Then gauge theories showed that symmetries can generate interactions. Now, information theory suggests that stability may be tied to how physical distinctions are protected across systems. The old image of objects carrying properties like labels is giving way to a world where relations, invariants, and distributed structure are often more fundamental than the object alone. A glass of water still returns us to the surface. It does not need quantum error correction to be held in the hand, but its stability is layered. Its atoms are stable, because quantum rules and electromagnetic interactions allow persistent structures. Its molecules hold together because charges and fields obey symmetries. Its macroscopic shape persists because many microscopic degrees of freedom cooperate into a solid boundary. Its rotation is constrained by angular momentum. Its thermal behavior is constrained by energy and entropy. Nothing about it is simple because nothing about stability is free. The quietest objects are often the ones most deeply protected. But protection also raises a new question. If information can be preserved by being spread into relationships, what happens in the one place where ordinary locality seems to break our ability to retrieve it? What happens when matter, radiation, charge, energy, and quantum states cross a boundary from which no signal can return. A conservation law tells us the account should not simply vanish. Quantum theory tells us information should not be erased from a closed system. General relativity tells us there are horizons. At that boundary, symmetry, conservation, gauge structure, and information stop being separate ideas. They are forced into the same problem. What does nature protect when even light cannot bring the record back? A boundary that no signal can cross is not just a wall, it is a challenge to the idea that physics keeps records. In ordinary life, losing a record means something practical. A page burns, a hard drive fails, a sound fades into the room. The pattern is gone for us, because no human instrument can reconstruct the exact previous state. But physics uses the word loss more carefully. When a book burns, the ink does not vanish into non-existence. Its molecules react with oxygen, heat flows into the air, photons scatter away, ash forms, smoke rises, and the original pattern becomes dispersed through an enormous number of microscopic degrees of freedom. Recovering the book would be impossible in practice, but the laws of microscopic physics do not simply erase the distinction between one book and another. A black hole makes that familiar kind of loss look too gentle. Matter can cross an event horizon, and after that crossing, no light signal from its later path can return to the outside. The horizon is not a solid surface, not a membrane a falling object must strike. For a very large black hole, crossing the horizon might feel locally uneventful to someone falling freely. But globally, the boundary is decisive. Outside observers can no longer receive messages from the object's future. The record has entered a region cut off from ordinary communication. In classical general relativity, the outside description of a settled black hole is startlingly sparse. It can be characterized by mass, rotation, and electric charge. The detailed structure of what formed it seems absent from the exterior. A collapsing star, a cloud of gas, radiation, dust, or a complicated arrangement of matter may all settle into a black hole with the same few external numbers. The shape of the original object, its chemistry, its internal patterns, its microscopic distinctions, all of these appear hidden behind the horizon. That would already be strange, but quantum theory makes it sharper. Black holes are not completely black. When quantum fields are studied on the curved space-time around a black hole, they lead to Hawking radiation, a faint thermal emission associated with the horizon. For a large astrophysical black hole, this radiation is incredibly weak, far colder than the cosmic background around it. But in principle, over immense timescales, Hawking radiation allows a black hole to lose mass. If it continues long enough, the black hole could shrink. Then the question becomes unavoidable. If the black hole evaporates, what happens to the information about what fell in? The simple answers are both painful. If the information is destroyed, then quantum mechanics loses one of its deepest forms of accountability. The evolution of a closed quantum system is supposed to preserve distinctions between possible initial states. A pure state may become scrambled into an almost unreadable pattern of correlations, but it should not collapse into a final state that contains no trace of which beginning produced it. If black holes truly erase information, the rules of quantum theory need to be changed at a fundamental level. If the information is not destroyed, it must come out somehow, or be encoded in a description that classical geometry does not reveal. The outgoing Hawking radiation initially appears thermal, as if it carries temperature but not detailed memory. A purely thermal glow would be like smoke, with no recoverable relation to the text of the burned book. Yet if quantum mechanics is right, the final radiation cannot be completely indifferent to the initial state. Somewhere in the correlations, the account must still balance. This is the black hole information problem. It is not a vague puzzle about cosmic darkness. It is a collision between four structures that each work extremely well in their own domain: general relativity, quantum field theory, thermodynamics, and the quantum principle that information is preserved in the evolution of closed systems. The horizon is where they are forced to speak at once. Thermodynamics enters because black holes have entropy. Entropy is often described as disorder, but that is too loose for the job here. More precisely, entropy is connected to the number of microscopic states compatible with the same macroscopic description. A container of gas can have the same pressure, volume and temperature, while its molecules occupy an enormous range of exact positions and velocities. The macroscopic variables are simple. The microscopic possibilities are vast. Entropy measures that hidden multiplicity. A black hole has a simple external description, but it also has entropy. And the remarkable part is where that entropy points. It is proportional to the area of the event horizon, not the volume hidden behind it. That is not how ordinary storage intuition works. A larger box holds more gas because it has more volume. A larger room holds more books because it has more interior space. But a black hole's entropy scales like a surface. This area law is not a decorative oddity. It suggests that gravity counts information differently. If one tries to pack more and more energy and information into a region, the region can eventually collapse into a black hole. The maximum entropy associated with that region then appears tied to the area of its boundary. The consequence is physical. Gravity may limit the amount of independent information that can be stored in a volume by the size of the surface enclosing it. The old picture says the contents of a region live inside the region. The black hole says the capacity of the region may be governed by its boundary. This is where the holographic principle begins. The name is dangerous if taken too visually. It does not mean that the world around us is a flat optical trick, or that solid objects are illusions projected from a cosmic screen. A hologram on a card is only a loose metaphor. The physical idea is narrower and more technical. In gravitational systems, the information describing a volume of space may, under certain conditions, be expressible in terms of degrees of freedom associated with a boundary. A boundary description is not automatically less real than a bulk description. It may be another language for the same physical content. One description uses depth, volume, geometry, and gravity. Another uses a lower dimensional quantum system without gravity. If the two descriptions are truly equivalent, neither is merely fake. They are different account books for the same underlying state. The strongest concrete example is the ADS/CFT correspondence. In this framework, a gravitational theory in a spacetime called anti-de Sitter space can be equivalent to a conformal field theory on its boundary. Anti-de Sitter space is not the spacetime we observe on cosmic scales in any simple way. It has a different kind of curvature and boundary structure from our expanding universe. So ADS/CFT should not be turned into a claim that our cosmos has been proven to be holographic. The careful conclusion is both narrower and stronger. In some precisely defined theoretical settings, gravity in a volume can be mathematically equivalent to quantum physics on a boundary. That equivalence is enough to disturb the older intuition. If a gravitational bulk and a boundary quantum theory can describe the same physics, then spacetime geometry may not always be the most fundamental language. A black hole in the bulk can correspond to a thermal state in the boundary theory. A geometric distance in the bulk can be tied to patterns of correlation in the boundary system. A process that looks gravitational in one language can be described as ordinary quantum evolution in another. The word ordinary here needs care. The boundary quantum theory may be highly complex, strongly interacting, and mathematically difficult, but it does not contain gravity in the same direct way as the bulk description. That is the surprise. Gravity can emerge as a different face of quantum degrees of freedom. Geometry, which feels like the place where physics happens, may in such models be reconstructed from the behavior of a non-gravitational quantum system. This does not make space unreal. Temperature is real, but it is not a property of one molecule. Pressure is real, but it comes from countless molecular impacts. Sound is real, but it is not the motion of one air molecule alone. A property can be emergent and still have physical force. If geometry is emergent in some quantum gravitational settings, the distances and curvatures of spacetime may be real in the same large-scale sense. They would be effective descriptions of a deeper structure, not hallucinations. The mechanism connecting the deeper structure to geometry often involves entanglement. Entanglement is not a magical thread for sending messages faster than light. It is a property of quantum states, in which the state of a combined system cannot be reduced to separate states of its parts. Measurements on separated systems can show correlations stronger than any classical hidden variable picture permits, while still respecting the no signaling rule. Entanglement is not communication. It is non-classical correlation built into the state itself. In holographic theories, entanglement becomes geometric. The entanglement entropy of a region in the boundary theory can be related to the area of a surface in the bulk geometry. That sentence is technical, but its consequence is simple enough to feel. A quantity measuring quantum correlation in one description corresponds to an area in a gravitational spacetime in the other. Area, the same kind of quantity that appeared in black hole entropy, becomes tied to information-like structure. The area is no longer merely a shape drawn in space, it becomes a measure of correlation. This is one of the strongest signs that geometry and information may not be separate at the deepest level. In ordinary experience, distance comes first. Two objects are separated, and then they may or may not interact. In these theoretical models, the order can look reversed. The pattern of quantum relationships helps determine the geometry in which separation is described. Systems that are strongly connected by correlations may appear closer in an emergent bulk. Systems with weaker or different correlations may appear farther apart. The analogy of a map built from travel times can help. If one knows how long it takes to travel between many cities, one can reconstruct something about their arrangement, even without seeing the map at first. Close cities tend to have short travel times, distant cities tend to have long ones. But the analogy fails at the important point. Cities already exist on a surface. In emergent spacetime, the surface may itself be the thing reconstructed from relationships. Another analogy is a woven pattern, but this too must be restrained. A tapestry's image appears because threads cross in a certain order. Cut too many threads, and the image fails. Yet the tapestry still lies in ordinary space. Quantum correlations do not sit inside the emergent geometry in the same simple way. In the strongest holographic examples, the geometry is a way of describing the organized relationships among quantum degrees of freedom. The threads do not lie in the picture. The picture is the large-scale form of the threading. This line of thought leads directly to quantum error correction. At first, error correction sounds like a topic for engineers, not black holes. A message is sent through a noisy channel. A memory device is exposed to damage. A computer must protect information from faults. The basic problem is simple. If part of a record is disturbed, can the original information be recovered? Classical error correction often uses redundancy. A bit can be stored in several places, or more sophisticated check structures can reveal where an error occurred. Quantum error correction is more delicate. An unknown quantum state cannot simply be copied, because the no-cloning theorem forbids making perfect copies of an arbitrary unknown quantum state. Instead, the information is encoded into correlations among multiple physical systems. Local errors can then be detected and corrected without directly measuring and destroying the logical quantum information. The key idea is that the protected information is not stored in one fragile location. It is spread across a structure. Damage to a small part does not necessarily destroy the logical whole. The information survives because it is encoded relationally. In holographic models, something similar appears. Information about a region of the bulk can be encoded in the boundary theory in a redundant way. It may be possible to reconstruct the same bulk information from different overlapping boundary regions. This resembles the logic of a quantum error correcting code, where losing some physical components does not necessarily erase the encoded state. The comparison is not a slogan. It is a mathematical insight developed inside specific theoretical frameworks. It also has a physical emotional force if kept clean. A black hole seems to hide information behind a horizon. Holography suggests that information in a gravitational region may not be stored where naive volume intuition expects. Quantum error correction suggests that the survival of information may depend on redundancy across correlations. Together, these ideas do not prove that the universe is a computer. They do something more precise. They show that the stability of spacetime descriptions may be tied to the same mathematical logic that allows quantum information to survive local damage. The horizon is not a hard drive. The boundary is not a literal screen. The radiation is not a readable text drifting outward in plain letters. But the black hole information problem forces physics to ask whether a record can be preserved when no single local place seems able to hold it in the classical way. This is where the book in fire analogy becomes useful again, but only after being corrected. A burning book loses its message for ordinary readers. The text becomes heat, smoke, molecular motion, scattered light. Yet the microscopic evolution may still preserve the distinctions in a fantastically scrambled form. With impossible knowledge, one could in principle trace the physical state backward. A black hole appears worse because the horizon prevents access to the interior. If it evaporates into radiation that looks thermal, the outgoing state seems to have lost the distinguishing marks of what fell in. The modern expectation in much of theoretical physics is that information is not truly destroyed, but saying that is not the same as explaining how. The question is how the outgoing radiation can carry enough subtle correlations to preserve the initial state, and how that can be reconciled with the smooth experience of falling through the horizon in general relativity. The demand is severe. The theory must preserve quantum unitarity without violently breaking the successful local predictions of gravity in ordinary regimes. A possible pattern emerges through time. Early Hawking radiation may look nearly thermal, carrying little obvious information. As evaporation proceeds, correlations between earlier and later radiation may become increasingly important. If the full process is unitary, the entropy of the radiation should not rise forever, as though information were being lost. It should eventually turn over and decrease in the precise sense associated with the page curve. This curve is not a photograph of a black hole. It is a theoretical diagnostic of whether information is preserved in the radiation. Recent theoretical work in simplified models has made progress in reproducing this kind of behavior using gravitational path integrals and structures often called islands. The details are highly technical, and they do not settle every question about real astrophysical black holes. But the direction matters. The calculations suggest that the naive semi-classical picture misses contributions that become important when one asks about the entropy of radiation after long times. The gravitational description may contain hidden bookkeeping terms that protect the quantum account. The word island has a misleading softness. It does not mean a literal island floating inside a black hole. It refers to regions included in the calculation of entropy in a way that can make the radiation's entropy follow the unitary page curve. The concept is mathematical, but its physical implication is sharp. The separation between what is inside the black hole and what is outside may not be as independent as classical geometry makes it appear, at least for the purpose of quantum information. This is not a finished theory of everything. It is a controlled sign that the information problem may be solved not by abandoning quantum mechanics, but by understanding gravity's quantum bookkeeping more carefully. The horizon may still be smooth for an infalling observer in the right conditions. The exterior radiation may still look thermal in coarse measurements, yet the fine-grained quantum correlations may carry the account that the coarse picture cannot see. Here, symmetry returns in a quieter form. The preservation of information in quantum mechanics is tied to unitarity, the structure that keeps total probability equal to 1 and maps distinguishable states in a way that does not simply erase them. It is not the same as Noether's theorem in the simplest mechanical examples, but it has a similar spirit of constraint. The theory cannot allow arbitrary loss without paying a price in consistency. The account must close somewhere, even if the closing is hidden in correlations far too complex to reconstruct. Probability itself is protected by the mathematical form of quantum evolution. If probabilities did not add up properly, measurement would lose meaning. If distinct states could collapse into identical final states under ordinary closed evolution, the theory would abandon its reversibility at the fundamental level. Black holes put pressure on this structure because their classical horizons seem to remove information from the accessible region. The information problem is therefore not just about one object in space. It tests the compatibility of quantum law with space-time geometry. A black hole is also a thermodynamic object. It has temperature, it has entropy, it can exchange energy. Thermodynamics is normally the physics of coarse descriptions, gas pressure, heat flow, temperature gradients. It does not track every molecule. Yet with black holes, thermodynamics touches gravity at the horizon. Temperature comes from quantum fields near curved spacetime. Entropy comes from area. Energy comes from mass. Information comes from the microscopic states required to explain entropy. 4 languages meet at one surface. If those languages are all correct in their domains, then the horizon cannot be only a geometrical boundary. It must also be a counting surface. It counts possible microstates through entropy. It shapes radiation through quantum field effects. It blocks classical signals. It exposes the limits of simple volume-based storage. The horizon becomes the place where symmetry's old lesson, what can change, what must remain, reappears in a more severe form. For matter falling inward, much can change. Form is destroyed. Chemical identity may be crushed beyond recognition. Radiation may be emitted before crossing. Tidal forces may stretch structures. The object's external individuality may disappear from the classical description. But if quantum mechanics holds, the distinction between possible initial states cannot be erased from the total final state. It must remain not as a recognizable object, but as information distributed in correlations. That word distributed is the bridge to error correction. In a quantum error-correcting code, the logical state is not accessible from every small part by itself. A fragment may contain almost no useful information, but a sufficiently large or appropriately chosen collection of parts can reconstruct the encoded state. The information is real, yet not localized in the naive way. It is protected by being spread. Holography takes a related structure and applies it to spacetime. Bulk information can be reconstructible from boundary regions in ways that resemble redundant encoding. A local bulk event may not correspond to one single boundary point. It may be encoded across a pattern of boundary degrees of freedom. If a portion is lost or inaccessible, the same bulk information may still be recoverable from another suitable portion. In the right models, geometry itself behaves as though it is supported by an error-correcting structure. The restraint is important. These results are best understood in specific theoretical settings, especially those connected to ADS/CFT. They are not a direct experimental proof of the microscopic structure of our universe, but their conceptual force is real. They give a working example in which spacetime, gravity, and quantum information are not separate subjects stacked beside each other. They are different aspects of one mathematical system. The old conservation laws were local enough to be heard in daily life. A recoil, a spin, a falling object warming the floor. The black hole version is far less accessible. No human can collect all Hawking radiation from an evaporating astrophysical black hole and decode the infalling matter. No laboratory can wait the required timescales. The information may be preserved in principle while remaining unrecoverable in practice. Physics often makes that distinction. What is impossible for us is not always forbidden by law. This difference between practical loss and fundamental loss is essential. A glass shattering on a tile floor is practically irreversible. The shards, sound waves, heat, and microscopic motions will not spontaneously reassemble into the original glass. Yet the microscopic laws may still be reversible at a deeper level. Irreversibility emerges from complexity, entropy, and our inability to track the exact state. A black hole threatens something stronger, not merely practical irreversibility, but possible fundamental erasure. That is why the problem matters. If quantum gravity resolves the information problem, it will likely do so by showing that the stronger threat was an artifact of using an incomplete description. The classical horizon and the semi-classical radiation calculation may both be accurate in their domains, but together they may miss the fine-grained structure needed for unitarity. The account did not fail, the ledger was incomplete. That phrase should be heard carefully. It does not mean every detail is already known. It means the pattern of modern results has shifted the pressure. Many physicists now expect that black hole evaporation is unitary in a complete quantum theory of gravity. The exact mechanism, especially in a fully realistic spacetime like ours, is still a subject of deep work. The more cautious reading is not that the puzzle is finished. but that the simple story of information disappearing into nothing has become harder to defend. The horizon still keeps its darkness in practice. If an astronaut crosses it, no message can be sent back. If a diary falls in, no external observer can open the black hole and read it. The classical causal boundary remains. What changes is the fine-grained accounting of the full quantum state. The diary's information, in this view, is not recoverable as a diary, not preserved in a human-readable form, not floating at the horizon as glowing text. It is transformed into correlations distributed across degrees of freedom that the classical picture cannot display. This is where the metaphor of memory becomes tempting and must be prepared carefully. A memory is not an object untouched by change. A memory survives because a physical system has been altered in a way that can later influence behaviour or be read out. A footprint in snow, a fossil in rock, a charge pattern in a memory chip, a synaptic change in a brain. All are traces. They do not preserve the event by freezing time. They preserve it by creating correlations between what happened and what remains. Physics can describe records this way. A detector click is a record because the detector's state becomes correlated with the incoming particle. A photograph is a record because light from a scene changed the chemical or electronic state of a surface. A gravitational wave detection is a record because passing curvature altered the relative lengths in an interferometer, and the instrument stored the resulting signal. The past is not held by magic. It is held by physical correlation. Black holes challenge this ordinary record-making because the horizon blocks direct access to the region where many correlations seem to go. If the object falls behind the horizon, the outside detector network cannot continue to monitor it. The record appears to be sealed. Hawking radiation then adds the threat that the seal itself evaporates. If all that remains is featureless thermal radiation, the physical correlation with the original object seems severed. The account loses the past. Holography and quantum error correction suggest a more subtle possibility. A record may survive without being locally visible. The information may be encoded in correlations that cannot be read from any small piece of radiation, any simple surface mark, or any classical interior picture. It may require the entire quantum state, or a reconstruction procedure available only in the complete theory. The past would not be stored as an object. It would be stored as relational structure. This idea connects back to symmetry because the distinction between real and redundant description is again central. A gauge choice may change the mathematics without changing the physical state. A boundary reconstruction may represent the same bulk content in different ways. Two descriptions that look unlike each other may be equivalent if they preserve all physical information. The account is not attached to one picture. It is attached to invariance across pictures. A conservation law once said, "Despite all visible changes, this quantity remains." Holography suggests a more radical version. Despite different descriptions of space itself, the physical content may remain. A bulk region and a boundary system can, in controlled cases, carry the same information. Geometry and quantum correlations become two languages for one state. The conservation of the account is no longer just energy or charge. It is the preservation of physical distinguishability. This does not mean everything reduces to information in a shallow way. A particle collision still has energy, momentum, spin, charge, and measurable products. A star still shines by nuclear fusion. A black hole still curves space-time. Information is not a replacement for physics. It is a way of describing what physical states can be distinguished, how they evolve, and how their correlations survive. The danger lies in turning information into a vague substance. The strength lies in using it as a precise constraint. The constraint is especially sharp at horizons. If the black hole has entropy, it has microscopic degrees of freedom. If it radiates, the radiation must be part of the accounting. If quantum mechanics remains unitary, correlations must eventually carry the distinction between possible origins. If holography is a guide, the boundary may encode bulk information in a distributed way. If error-correcting structure is relevant, locality itself may be emergent rather than absolute. Locality is the next pressure point. In ordinary space-time, local physics means that events are influenced directly by nearby events, and signals cannot outrun light. This principle is woven deeply into relativity and quantum field theory. But holographic encoding is non-local from the boundary point of view. A bulk event may be represented across many boundary degrees of freedom. This does not automatically allow faster-than-light signaling inside the bulk. The emergent geometry can still obey causal rules, but it means the underlying description may organize information differently from the geometry it produces. That's a difficult but important distinction. Non-local encoding is not the same as non-local signaling. A quantum error-correcting code can spread information across many physical parts without allowing any one part to send forbidden messages. Entanglement creates correlations but not controllable faster-than-light communication. Holography can encode bulk locality in a boundary theory whose variables are arranged differently. The appearance of local spacetime may arise from a deeper system that does not store information in the same local way. The consequence is not poetic. It is a demand placed on any theory of quantum gravity. It must explain why the world looks local when the deeper encoding may be distributed. It must explain why falling observers experience smooth horizons under appropriate conditions, while distant observers can still expect information to be preserved. It must explain why entropy scales with area, why radiation can carry correlations, and why the ordinary rules of causality survive in the emergent spacetime. A useful comparison comes from a library catalogue, though it is only a comparison. A book can be found through an author index, a subject index, a shelf number, or a digital record. These descriptions are different, and none is the book itself, but each can locate or reconstruct something about the same object. In holography, the contrast is far more radical because one of the descriptions includes an entire gravitational geometry, and the other may not. Still, the lesson is similar. The same physical content may be accessible through different organizational schemes. The black hole forces us to accept that the obvious scheme may not be the deepest one. The obvious scheme says information is inside the volume where the matter went. The entropy area law says the boundary matters more than volume intuition expects. Hawking radiation says the black hole can slowly give energy back to the outside. Quantum mechanics says the full distinction between initial states should not vanish. Holography says a boundary description may be complete. Error correction says a record can survive local damage by being spread through correlations. Each idea alone is powerful. Together they shift the idea of symmetry from sameness to accountability. Invariance gave energy. Gauge symmetry gave charge and interaction structure. Broken symmetry gave mass patterns and force ranges. Information preservation now asks whether even a black hole can be made accountable to quantum law. The question has become more severe, but the shape is familiar. What can change, and what is forbidden to disappear? At this point, the word source code might sound tempting again. It would be easy to say that the universe is written in hidden instructions, or that black holes reveal a cosmic program. But that language becomes unsafe if it replaces the mechanism. The actual physics is more demanding and less theatrical. Symmetries constrain equations. Gauge freedoms remove redundant descriptions. Entropy counts microscopic possibilities. Horizons define causal boundaries. Quantum error correction protects logical information by distributing it through correlations. Holographic dualities show equivalences between gravitational and non-gravitational descriptions in special settings. That is already strange enough. It does not need to be inflated. A title may call symmetry a hidden rulebook, but inside the science, the rulebook is not a literal object. It is the structure of transformations that leave physical content unchanged. A title may say, black holes keep a record, but the record is not a notebook at the horizon. It is a pattern of microscopic degrees of freedom and correlations that a complete theory must account for. A title may speak of information as if it were substance, but physics treats it as distinguishability, correlation, and state structure. The disciplined version is more durable than the sensational one because it survives contact with equations. Black holes are not evidence that reality is fake. Holography is not proof that the universe is a projection. Quantum error correction is not proof that nature is running software. The real claim is narrower. Some of the most successful theoretical tools for quantum gravity describes space-time and information in ways that are deeply intertwined. And black holes are the place where this intertwining becomes impossible to ignore. There is a quiet image in this, not a screen, not a program, not a hidden operator, but a sealed furnace at the edge of space-time's rules. Matter falls in. The classical description forgets almost everything except mass, charge, and spin. Quantum fields make the furnace glow faintly. Thermodynamics assigns entropy to the horizon's area. Holography asks whether the surface can carry the account. Error correction asks how an account can survive damage without being stored in one place. The black hole becomes less like a destroyer of law and more like a test of how law protects what cannot be seen directly. The test is still unfinished. The exact microscopic degrees of freedom of black holes in our universe are not fully known. The complete theory of quantum gravity remains beyond experimental confirmation. The strongest holographic examples live in spacetimes different from the one cosmology seems to describe. The Page curve has been reproduced in important theoretical models, but not by watching a real black hole evaporate to completion. The evidence is mathematical and indirect, not observational in the everyday sense. But unfinished does not mean empty. The constraints are real. A theory that destroys information must explain how quantum mechanics changes. A theory that preserves information must explain how the correlations escape the naive horizon picture. A theory that uses holography must explain how our kind of spacetime fits, if it fits at all. A theory that invokes error correction must show how the protected encoding arises physically, not merely by analogy. The problem has become precise enough that vague wonder is no longer useful. Precision gives the mystery its shape. A black hole is measured by mass, spin, and charge, but its entropy demands microscopic states. Hawking radiation is nearly thermal, but unitarity demands fine-grained correlations. A horizon blocks signals, but holography suggests boundary accounting. Geometry looks local, but quantum encoding can be distributed. Each pair creates a tension with a physical consequence. None can be resolved by saying the universe is simply strange. The glass first turned in the hand is far away now, but not gone. When it rotated, the law did not change, and angular momentum entered the account. When fields transformed internally, charge entered the account. When spacetime curved, energy became more subtle. When black holes evaporated, information itself entered the account. The motion has been one long expansion of what it means for physics to keep track. At human scale, the account is simple enough to trust. A glass falls and warms the floor. A lamp emits photons. A hand turns, and muscles do chemical work. A radio signal travels through electromagnetic fields. Nothing about this needs a black hole, yet the same insistence on accountability reaches the most extreme object allowed by gravity. It asks whether even a horizon can make a physical distinction disappear from the final state of the world. If the answer is no, then information is not merely another quantity on a list. It is part of the framework that tells physics what it means for one state to become another. Conservation laws began as balances of energy and motion. In black hole physics, the balance reaches into distinguishability itself. The universe may transform states beyond recognition, but a complete quantum description should not confuse different beginnings as though they were the same. This is the step that leads beyond black holes. A record does not have to be readable to exist. It can be microscopic, distributed, scrambled, encoded in correlations protected by symmetry, or hidden behind a description that has to be translated. The physical world is full of traces that survive by becoming something else. A fossil is not the animal. A photon pattern on a detector is not the star. A memory in a brain is not the event it remembers. Yet each is a structured consequence of an interaction. The next question has to be handled gently, because it touches the listener more directly than a horizon does. If physics is a science of records, correlations, and transformations that preserve distinctions, then a mind is not outside that physics. It is a system that stores traces, updates states, loses some correlations, strengthens others, and turns physical records into experience. That does not mean consciousness controls quantum reality. It does not mean thought rewrites the laws. It means the path from symmetry to information eventually returns to the creature asking the question. What is a memory, if every record in nature is a physical trace of what was allowed to change without being completely lost? A memory is not a small object stored intact inside the skull. It is not a sealed drawer, not a photograph placed in a hidden room, not a perfect replay waiting for a signal to open it. In the brain, memory is physical, but its physical form is distributed and active. It lives in change connections between neurons, altered strengths of synapses, patterns of excitability, molecular traces inside cells, and networks that can be reactivated in new contexts. That already makes memory more like the rest of physics than it first appears. A record is not the event itself. A footprint is not the foot. A fossil is not the animal. A detector click is not the particle before detection. A memory is not the past, preserved untouched. It is a present physical state shaped by a past interaction. It is a correlation between what happened and what remains. The brain makes these correlations through mechanisms that are biological, chemical, and electrical. Neurons send signals through voltage changes across membranes. Synapses alter the probability that one neuron will influence another. Proteins are made and modified. Networks become more likely to produce certain activity patterns again. A remembered place, face, sound, or fear is not held by one isolated neuron like a label pinned to a wire. It is carried by relationships across a system. This does not make memory unreal. It makes memory fragile and powerful in the same way many physical records are fragile and powerful. The stored pattern can degrade. It can be revised when recalled. It can be strengthened by repetition or weakened by interference. The brain is not a passive archive. It is an organism maintaining useful traces under constant noise from metabolism, sensation, emotion, sleep, and time. The mismatch is immediate. Ordinary intuition says a memory should either be there or not there, like a file on a shelf. But actual memory is more like a living constraint on future activity. It changes the probability of what the brain will do next. It influences recognition, action, expectation, and emotion. It preserves enough of the past to guide the organism, but not as a perfect copy. If memory required perfect storage of every microscopic detail, biological life would collapse under its own records. If it preserved nothing reliably, learning would vanish. The mechanism is neither mystical nor simple. It is plasticity, the capacity of neural systems to change their structure and function in response to experience. When an event matters, the nervous system does not save the event itself. It modifies itself so that later signals travel through a changed landscape. The record is in the altered routes, thresholds, connections, and coordinated activity. The past survives as a physical bias in the present. This brings the question back to information in its clean physical sense. Information is not a ghost floating above matter. It is the distinction between possible states. A neuron that fires differently after training carries information, because its state helps distinguish one history from another. A synapse strengthened by repeated activity carries information because it changes what future activity can occur. A brain state carries information because it is not interchangeable with every other brain state. But the brain also reminds us that information preservation is never free from thermodynamics. Neural activity consumes energy. Ion gradients must be restored. Molecules must be synthesized and degraded. Heat is released. The body has to keep the tissue alive, oxygenated, regulated, and repaired. A memory may feel weightless, but the system that supports it is not. It is warm, wet, chemical, noisy, and expensive. This is one of the quiet connections between mind and physical law. To remember is not to step outside physics. It is to use physics in an organized way. A brain maintains order locally by consuming energy and exporting entropy to its surroundings. It can preserve useful correlations because the organism is not a closed equilibrium system. It eats, breathes, circulates blood, releases heat, and repairs itself. The mind stability depends on a river of physical exchange. That does not reduce experience to a trivial mechanism. The subjective feeling of remembering, the inner presence of an image, the emotional weight of a voice or place, remains one of the deepest open questions in science and philosophy. But the responsible boundary is clear. There is no scientific basis for saying that consciousness directly rewrites quantum laws or creates external reality by observation in the everyday human sense. The brain is a physical system inside the universe, not a magical exception to it. The more interesting fact is narrower and stronger. A system made of matter can become structured enough to hold records of the world, compare them, use them, and discover abstract relationships that are not visible to the senses. A brain can turn repeated experience into expectation. It can turn expectation into experiment. It can turn experiment into law. And in rare cases, it can discover a theorem showing why laws that ignore certain transformations must preserve certain quantities. That is not a proof that consciousness is fundamental. It is evidence that physical systems can become capable of recognizing physical structure. The mind that understands symmetry is itself made possible by symmetry-governed physics. Neurons depend on ions, charges, molecular bonds, and energy flow. The body depends on chemistry. Chemistry depends on quantum states and electromagnetic interaction. Electromagnetism depends on gauge structure. Energy metabolism depends on conservation and thermodynamics. The act of thinking about Noether's theorem is carried by matter that obeys the kind of constraints the theorem helps explain. There is something almost circular here, but not in a mystical sense. The universe produces stable structures because its laws have symmetries and conservation principles. Some stable structures become living systems. Some living systems develop nervous systems. Some nervous systems become capable of abstract mathematics. Then mathematics reveals why stability and conservation were possible in the first place. The loop is not an argument that the cosmos was aiming at us. It is a physical fact that intelligibility can arise inside an intelligible world. That point needs restraint. It would be too easy to say that the universe wants to know itself, or that consciousness is the final purpose of symmetry. Those are philosophical interpretations, not scientific conclusions. The safer statement is more exact. The laws that make matter stable also make memory, measurement, and science possible. Without conservation, there would be no reliable machines. Without gauge structure, no familiar atoms. Without thermodynamic flow, no living metabolism. Without neural plasticity, no biological learning. Without memory, no cumulative science. Science begins when records become trustworthy enough to compare. A mark on paper, a number in a notebook, a signal in a detector, a trace in a photographic plate, a stored waveform from an interferometer, a brain remembering an anomaly. Each is a physical record. It lasts only because matter can hold structured differences over time. That ability is not separate from the laws being studied. It is one of their consequences. This is why the history of symmetry is also the history of measurement. A conservation law is not just an elegant sentence about the universe. It lets experiments be repeated, results be checked, errors be found, instruments be calibrated. If the same apparatus under the same conditions gave different laws depending on the day, science would fragment. If the same particle interaction refused to obey charge conservation, detectors would lose their grammar. If energy could appear without constraint, the difference between signal and mistake would blur. The reliability of records depends on the reliability of transformations. Move an apparatus and the law should not change just because it is elsewhere. Wait an hour and the law should not rewrite itself without cause. Rotate a detector, and the underlying physics should not invent a new direction unless a real physical field or condition breaks that symmetry. Experimental science relies on these assumptions every moment, often without naming them. The noisiest laboratory still depends on deep indifference. The table vibrates, the electronics drift, the room warms and cools, particles scatter, background radiation passes through walls, human hands are imperfect, yet the laws do not care which page of the notebook is used, which coordinate axis is drawn, or which arbitrary second is called zero. The experimenter fights noise while relying on symmetry. Measurement is possible because not everything changes when the description changes. This is another way to see why error correction felt so natural in the previous layer. All records live under attack. Heat, noise, decay, friction, imperfect instruments, forgetting, radiation damage, computational errors, environmental coupling. A stable record must either be protected, refreshed, redundantly encoded, or short-lived enough for its purpose. Biological memory uses repetition, consolidation, and network structure. Digital memory uses error-correcting codes. Quantum information uses more delicate encodings to protect states from decoherence. Physical law uses symmetry to protect certain quantities from arbitrary change. These are not the same mechanism, but they rhyme because they answer similar pressures. How can something meaningful survive disturbance? How can a system change without losing every trace of what came before? How can a present state remain connected to a past state when the world is constantly moving, heating, colliding, radiating, and forgetting? The answer is never that nothing changes. The answer is that some structures are constrained through the change. A memory is constrained change. A conservation law is constrained change. A gauge invariant quantity is constrained description. A black hole information problem is constrained ignorance. A physical theory is the attempt to say exactly which constraints nature obeys. This is where the language of computation becomes tempting again. A computer also preserves and transforms information according to rules. A program changes states step by step. Error-correcting codes protect messages. Digital systems make it natural to imagine that reality itself might be computational. Some serious philosophical and theoretical ideas explore this possibility in different forms: digital physics, mathematical realism, informational approaches to physical law. And simulation hypotheses, they are not all the same claim. They must not be collapsed into a single dramatic sentence. Discrete physics does not automatically mean simulation. Information playing a central role does not automatically mean a computer in a higher universe. Mathematical structure being astonishingly effective does not prove that mathematics alone is the substance of reality. A simulation hypothesis is not the same as a gauge symmetry, a quantum code, or a conservation law. These ideas may touch one another in speculative discussion, but they do not stand on the same evidential ground. The disciplined conclusion is more interesting than the exaggerated one. Modern physics increasingly finds that laws, symmetries, entropy, and information cannot be kept in separate boxes. Conservation laws arise from invariance. Gauge symmetries shape forces and charges. Black hole entropy ties area to microscopic states. Holographic theories relate geometry to quantum information in controlled models. Error correction shows how information can be protected by distributed structure. None of this proves that the universe is a laptop, a program, or a projection. It shows that the older image of matter moving through empty space under externally attached forces is too shallow. A better image is a woven constraint, not a cloth lying inside space, but a pattern of allowed transformations and preserved distinctions. The world can change in countless ways, but not in every way. It can burn, fall, scatter, decay, radiate, remember, and forget. Yet each process is shaped by restrictions. Some quantities cannot change without exchange. Some descriptions cannot be counted as different worlds. Some information may be scrambled without being destroyed. Some symmetries may be hidden in the state while remaining present in the law. This pattern is not known completely. That matters. Physics is strongest when it knows the boundary between mechanism and speculation. We know Noether's theorem as a precise mathematical result within its domain. We know conservation laws are tied to symmetries in the relevant theories. We know gauge symmetries organize the standard model. We know black holes have thermodynamic behavior in theoretical physics, including entropy proportional to a horizon area. We know holographic dualities work in certain mathematical settings. We do not know that our entire universe is literally a quantum error-correcting code. We do not know that space-time in our cosmos emerges exactly as in anti-de Sitter models. We do not know that information is ontologically primary in the strongest philosophical sense. But uncertainty here is not emptiness. The narrower facts already carry force. They show that the physical world is not held together merely by objects bumping into objects. It is held together by invariances, constraints, fields, correlations and accounts that remain meaningful through transformation. The old mechanical image remains useful at the scale of wheels, levers, falling stones, and everyday motion. It is not false there. It is simply not deep enough to explain why its own regularities hold. The final layer is therefore not a new topic, but a return to the first gesture with more behind it. A glass turns in the hand, the reflection moves, the water trembles, muscles contract, chemical energy is converted, nerves fire, the brain predicts the weight and corrects the grip. Angular momentum is accounted for. Electromagnetic interactions keep the glass solid. Quantum states keep the atoms stable. Gauge symmetries protect charge. The memory of the action modifies neural circuits. Heat leaves the skin and glass. Nothing in the scene is outside physics, yet the scene is full of preserved structure. The hand does not need to know the theorem to obey it. The water does not need to know symmetry to respond to rotation. The atoms do not need to know gauge invariance to hold their charges. The brain does not need to know thermodynamics to spend energy remembering. Nature does not follow laws because they are written in human language. Human language became capable of describing them because the world is consistent enough for description to survive. That consistency is the quiet miracle, though not a supernatural one. It is the physical condition under which science can exist. If every event were isolated from every other by lawless change, no record would accumulate. If every transformation erased all structure, no memory would guide action. If every description were equally physical, no invariant would remain to measure. The universe is knowable because it is not arbitrary. It changes, but not without structure. Noether's theorem gives one of the clearest windows into that structure. It does not say that everything is symmetric. It does not say that all quantities are conserved in all situations. It says something more exact and more useful. When a continuous symmetry is present in the right kind of physical system, a conservation law follows. That sentence contains both power and humility. Power, because it connects the visible behavior of systems to hidden invariants. Humility, because it tells us to check the symmetry before claiming the conservation. That humility becomes essential in the largest and smallest domains. In an expanding universe, global energy requires care. In quantum fields, particles are excitations rather than little classical beads. In gauge theory, different descriptions may represent the same physical state. In black hole physics, the boundary between known and hidden information becomes a test of quantum law. In the brain, memory is physical, but not photographic. Each case asks us to stop trusting the simplest image and look for the deeper invariant. The story also changes how we remember the people who made the structure visible. Emmy Noether's work became part of the machinery of modern physics, while her public name remained far less familiar than the consequences of her theorem. That fact should not be turned into myth. It is not a cosmic pattern of hidden discoverers. It is a human pattern of institutions, memory, prejudice, abstraction, and storytelling. The mathematics survived because it was correct and useful. The recognition moved more slowly because human memory is less clean than physical law. There is an austere fairness in the theorem itself, even if history around it was not fair. The theorem does not care who writes it on the board. It does not care which language names it. It does not care whether the room recognizes the person who saw it. If the symmetry is there, the conserved quantity follows. The structure is impersonal. The act of discovering it was deeply human. And that is perhaps the most fitting way to hold the ending. The universe is not made more trustworthy by being made more sentimental. It is trustworthy where its laws are stable, where transformations leave the right things unchanged, where measurements can be repeated, where records can persist, where symmetries protect accounts from dissolving into noise. Human beings enter that world as physical systems that can remember, calculate, overlook, correct. and eventually understand part of the order that made understanding possible. The deepest question does not vanish, it becomes quieter. Beneath every ordinary change is the question of what did not change. Beneath every conservation law is a symmetry. Beneath every measurement is a record. Beneath every record is a physical system holding a distinction against time, noise, and heat. And beneath the act of knowing any of this is the same accountable universe, one that turns, burns, curves, scatters, and remembers through structure, never giving a certainty beyond its evidence, but giving enough invariance for a glass in the hand to become a path toward the hidden grammar of reality.